Welcome to the community of
engineers, the change agents in the society.
In this video, we will discuss torsion. Torsion is simply the twisting of a component or part. As engine transmits torque on the shaft, consequently differential creates an equal and opposite torque. The stress and strain analysis would be performed in a circular cross section of member subjected to twisting couples or torque. The couples have same magnitude but in opposite direction. Right hand rule may be used to represent the loading. When circular shaft is subjected to torsion, every cross section remains plane and undistorted, means cross section rotates as a solid rigid slab. This property allows to determine the distribution of shearing strains in a circular shaft. Now consider a shaft AB subjected to equal and opposite torques T and T dash at point A and B. Now cut a section perpendicular to the axis at C. Now consider a portion BC and we can see the shear force that is acting on the plane of portion BC at point C. Further, it includes the elementary force dF perpendicular to the radius of the shaft. Equilibrium condition requires that the dF should be equivalent to the internal torque T, whereas here this rho is the perpendicular distance from the shear force dF to the shaft axis. Now sum of moments of the shearing forces dF equals to the torque T. So integral rho dF is equal to the torque T. Since dF is equal to tau dA, where tau is the shear stress on the elemental area of dA. Thus we can rewrite the expression as integral rho tau dA is equal to the torque T. However, the expression here does not tell how the stresses are distributed in the cross section. For that, now the deformations in the circular shaft. Now consider an intermediate surface for the analysis. Upon twisting, there will be some bend in the surface. The angle produced due to this bend is actually the shear angle. Now here this gamma is the shear angle which is the shear strain. At the same time, there is also a twist, and this phi is the twisting angle. And this rho is the distance from point to the axis of the shaft. Now consider here arc A dash, as we can write this A dash is equal to the length of the shaft with the shear angle gamma. Also we can write this arc A dash as rho phi. Thus we can write this expression as L gamma is equal to rho phi. So the shear strain is equal to rho upon L phi. Let's say this is expression 1, and for the maximum shear strain, we can write the expression as gamma max is equal to C upon L phi, and this is expression 2. Here C is the radius of the shaft. Now to eliminate phi from the equations, let's write same expressions as phi is equal to gamma L upon rho, and phi is equal to gamma max upon C L. So we can write as gamma L upon rho is equal to gamma max upon C L. Thus for the shear strain, gamma is equal to rho upon C gamma max. Let's say this is expression 3. Now here we can see that this expression indicates that shear strain varies linearly with the radius. Now to see the stresses within the elastic range, assuming all the shear stresses in the shaft remains below the yield stress, means shear stresses remain below the proportion limit or elastic limit. So using Hooke's law as tau is equal to G gamma as sigma is equal to E epsilon. Here E is the modulus of elasticity. Similarly, here G is the modulus of rigidity. Now coming back to the same expression as gamma is equal to rho upon C gamma max. Now multiplying G on both sides, the modulus of rigidity, this G gamma is equal to rho upon C G gamma max. Now considering Hooke's law, we can rewrite the expression as tau is equal to rho upon C tau max. Now similarly, again we see that shear stress at every point or at any point varies linearly with the radius of the shaft. Here shear strain is more important from the design point of view once the loads are applied to the member. Now considering a solid shaft and hollow shaft, an expression is tau is equal to rho upon C2 tau maximum for the case of solid shaft and tau minimum is equal to C1 upon C2 tau max. Now here C1 is the inner radius and C2 is the outer radius of the shaft. Again this rho is any distance from the axis of the shaft. Now recall the previous expression. Recall as integral rho tau dA is equal to tau T. Here this is tau dA is the shear force dF. The sum of the moments of the elementary forces dF that is must equal to torque T. Now we can write this expression as torque is equal to integral rho tau dA. Further, we can write as, considering this previous expression, that rho upon C tau max dA, as tau is equal to rho upon C tau max. Or we can write as T is equal to tau max upon C integral rho square dA, whereas this rho square dA is J, which is polar moment of inertia. So this entirely depends on the geometry of the cross section, where the integral represents the polar moment of inertia, that is J, of the cross section with respect to the center O of the axis. Now this polar moment of inertia represented with symbol J is the mere of the shaft's ability of the shaft's ability to resist torsion. Now we can write this as the same expression, T is equal to tau max upon C J, polar moment of inertia, or we can write as tau max is equal to Tc upon J. Now this expression is known as the elastic torsion formula. And for shear stress at any distance rho, we can write same expression as tau is equal to T rho upon J. Now this is for the case of for shear stress at distance rho. Now to calculate the polar moment of inertia for the case of or for solid shaft, this J is equal to half pi C4, and for the case of hollow shaft, this J is equal to half pi C is power 4 minus C1 is power 4. Now here this is the outer radius and this C1 is the inner radius of the shaft. As far as units are concerned, torque is with Newton meter, rho or C is in meters, polar moment of inertia J is meter raised power 4 and tau is Newton per meter square or as Pascal. Now we will end our discussion here.